Hello, can you hear me?
Hello, great, thanks. So I am ready to stream your presentation.
Is sound okay?
Mm-hmm.
Okay. So let's start. Hello, everyone. My name is Akzharkyn. Um, this break, I graduated from Nazarbayev University with a master's degree in electrical and computer engineering. So, as a part of master thesis, I wanted to do some mix of computer vision and natural language processing. That's why I have chosen this project, video description generation. And today I'm going to show some small part of my master thesis. So here's the outline of today's presentation. First, I'm going to talk about what's video description, why do we need it, and then show steps for feature extraction, then introduce two neural network models, show evaluation metrics used to evaluate the performance of the models, give results, and demonstrate video description algorithm. So what's video description? It's just a generation of text that describes the video content. There are different applications of video description, such as human-machine interface, automatic video subtitling, some surveillance systems, video-to-text processing. Highly efficient video description can be useful in different applications. For example, in surveillance cameras, for example, for automatic detection of the scenery, for generating description of the scenery. With the recent developments in the field of deep learning, there was progress in the video description. However, there is still a significant gap between the accuracy of the currently available methods for automatic video description and the performance of these tasks by human. That's why this task is challenging, but at the same time is interesting. So here's the methodology. So flowchart showing the basic steps for video description. So first we have video input. We need to extract features from the video. Then we should train neural network. And for this project, I used two types of neural network, sequence to sequence and attention mechanism. And then we generate text, like which describes the video. So now let's look at each of these steps. So first step is feature extraction for video. So video basically is a sequence of frames. That's why we use frame to extract features. So for each video, I've used 40 frames. And we pass these frames through the VGG16 network. VGG16 is a very popular neural network that was trained on huge data set, like on data set with about 14 million images from different classes. And it's mostly used for transfer learning, so for feature extraction. This network consists of different layers of convolutional and max pooling with a different number of channels. Since this network was trained for classification, the last layer is softmax layer. However, for our task for video feature extraction, we don't need classification part. So just pass each frame through the VGG16 network till the last layer. So each frame will be represented by a feature vector of size 4096. So for each video, I use 40 frames, and each frame is represented by a vector of 4096. Next, text. Since we need to train our model to generate text, we should give input in terms of text. However, we cannot input just raw text. We need to pre-process it and give in terms of numerical values. So this process is called vectorization. So for example, we have sentence, kids are talking about the rain. Then we do some pre-processing. We just do lowercase. We remove some extra spaces, numbers, symbols, special symbols, and add this at the end and at this beginning and at the end of sentence. We add these tokens. I will explain later why do we need them. And after that, we do tokenization. So tokenization is a process of representing sequence in terms of smaller parts. So in our case, we use words. So sentence, we represent sentence as a sequence of words, and we give index for each unique word is represented by some index, unique index. So here, for example, this sentence now look like this after tokenization. And then in order to input to the model, we convert to vector. There are two ways. First is to train our own embedding layer, or another method is use already pre-trained Glove database, which has vectors for each word in the dictionary. So after this step, each word will be represented as a vector. And the size of the vector we define by ourselves, by training, by adjusting the parameters. And so our initial sentence now look like this, as a list of vectors. Let's see. So before going to neural network, let's quickly recap some basic LSTM layer. This layer is a special stands for long short-term memory. It's a special type of recurrent neural network. It's just a chain of blocks. So each block has its own input, hidden states, cell state, and 3 gates. Forget input and output gates. So, for example, at time step T, we have input if X. Then we decide which part of the cell we should forget, which part of the new input we should pass to that cell state, like add to memory. We also generate some candidate cell states, and then we decide which part of the new information we will pass to the next time step, like we'll output to the next time step here. So all of these gates are just some dense layers. So for example, with sigmoid or hyperbolic tangent. And next is gated recurrent unit. It's similar to LSTM. It has also chain of blocks, but in contrast to LSTM, has only reset and update gates. So we have our input at time t, and then reset gate decides whether to remove some part of the previous hidden state here. And then update gate decides whether to add input, how much of input should be added to the hidden state, and it will be sent to the next time step. So for example, when update gate value is 1, the hidden state will be equal to the previous hidden state. And when update value is 0, it means we will consider new input. So here's the first neural network model, sequence to sequence. It consists of 2 parts, like encoder and decoder. Why it's called sequence to sequence? Because from sequence we generate another sequence. So in our case, in our project, input sequence is just sequence of frames, and output is text in terms of sequence of words. So encoder and decoder, they consist of LSTM layers. So we have 40 time steps. So I used 40 frames, and I just have like input them a different time step. And in the decoder, I also have 40 time steps, because the length of the text of the sentence generated by the model will be 40, like maximum 40 words will be generated. So let's start with encoder. Let's look at encoder. We have our input, like frame 1, frame 2, and we have hidden states of LSTM layer. Each LSTM at each time step has 40 units. And then we pass our inputs through the layers and obtain the last hidden state. And this hidden state will be used as input to the decoder. And this hidden state is actually a vector which stores information about the input, our input frames. Remember embedding layer, so we also have text, and we need to insert text to our model. That's why we pass our sentence through the embedding layer. So 28,366 is the vocabulary, dictionary size. So it means our model knows only this much of words. And so after embedding layer, we obtain like vectors for our words. So first input to the decoder is always start sequence talking. Because we need to let the model know where the beginning and end of the sentence. And the last word will be always end sequence. So we have input, and for inference stage, we take the output of the previous time step as input to the next here. V2, for example, generated by the first time step, is used as input in the next time step, and so on. And at the end, we have dense layer. So as I mentioned, there are like 28,366 words, and the dense layer decides whether the generated given word belongs to one of them. Just has a softmax activation function for probability distribution. This one is for inference stage, but for training stage, we know our output. We know what sentence should our model generate for the given input, and that's why when we pass input to the decoder, we take them from the labels, from the known sentences, given sentences, reference sentences, not from the hidden state output of the previous time step. And the difference between training and inference stage can be seen here. So here's the code. So for training stage, first we have input. We have 40 frames with size 4096. Then for encoder, we use LSTM with 40 units. Then we pass our image input to the encoder. And we obtain encoder states. Because we need encoder states because we pass the last encoder state to the decoder. So then we have embedding layer. Used 256 units, means each word is represented by a vector of 256. Then have decoder. We define decoder is also LSTM with 40 units. And here we can see that initial state of our LSTM is actual encoder state. Then we have dense layer with softmax, and we obtain our output. So inputs to the model during training is just images like frames. to be exactly features, image features, then language input, like the output of the embedding layer, and output is the output of the dense layer. But for inference stage, we pass the not the here for decoder, we pass decoder state inputs, and because we pass the output of the previous time step to the next time steps. That's why we have decoder state inputs here. Here we can see that's for sequence to sequence model. And attention mechanism, attention network is very similar to sequence. It's just some transformation of that because it considers the context vector. So if in previous sequence to sequence model we pass inputs and obtain and take the last hidden state of the encoder and pass it to the decoder. In this case, in attention mechanism, we use inputs all the time, like information about inputs at each time step. So, for example, in sequence to sequence, only one vector is used to represent input. And sometimes some early frames can be, the information about early frames can be missed, but in attention mechanism, we keep this information. And why it's called attention? Because it means like it shows how much attention network should pay to the encoder, to the input, in order to give the current output. So we have 40 frames, for example, and first we calculate score. We use outputs of the encoder, like hidden states of the encoder, and hidden state of the decoder at current time t. The score is computed by using dense layers. So we have a separate dense layer for encoder and for decoder. And then we apply softmax in order to have values from 0 to 1. So our attention weights will be from 0 to 1. And then we can calculate context vector. So why from 0 to 1? So if attention weight is 1, for example, for time step for encoder input 4, means that in order to predict current output, the network should pay more attention to the input number 4, and the rest can be ignored. So that's how we calculate context vector, and then we use this context vector and concatenate with the current, with the previous output of the decoder, and obtain new input to the decoder. So and so on. So this information, like for the next time step, we again calculate score, softmax, attention weight, the context vector, and obtain new input. And the main difference also is in the layer that I used. So for attention mechanism, I'm using gate to current unit for encoder and decoder. The reason is because attention mechanism requires more training because we have additional 3 dense layers, and gate to current unit has less parameters than LSTM. And that's it for the second model. And now here is the code. So how attention unit is implemented. This kind of attention unit is called additive because we add the encoder and decoder hidden states. It was introduced by Bogdanov. That's why it's called after his name. So we have dense layers, and here we just add. So we have values like weights for encoder hidden state, for decoder, and we then train again another dense layer, apply softmax, and we multiply attention weights by the values by encoder hidden states, and reduce sum is done to sum up across the time step. So we sum up across the axis one. In order to evaluate and to know how good our model at generating captions, we should use some metrics. And one of the popular metrics used in evaluation of machine translation is BLUE, bilingual evaluation on the study. This metric just evaluates how close the generated sentence to the reference sentence by matching, by calculating the number of matches of n-grams. So, for example, we have our candidate sentence just generated by our model, and we have reference sentence. And we compare them and calculate how many matches of, for example, one word, of two words, of three words, or four words between them. Then we calculate brevity penalty, if the length of generated sentence and reference sentence are different. And finally, we obtain BLUE score by using geometrical mean. And so the value of one of the BLUE metric means that the generated caption total is totally identical to the reference caption, and zero means that there are any words that match in both sentences. The problem with BLUE is that it considers exact matching. So in order to obtain one means like the words should be identical. That's why another metric was introduced called Meteor. This metric is considers not only exact matches, but stemmed words, synonyms, paraphrased matching. For example, when we have when two different person describes the video, they can use like different words, but the meaning can be the same. So for such cases, Meteor is more useful than BLUE. And so it also counts matchings. First, we find the number of mapped unigrams. Like by unigrams means word. So how many words in both sentences the same. Then we find precision and recall for generated sentence and for reference sentence. Then find fragmentation ratio. Calculate the harmonic mean. Here, fragmentation ratio is calculated by using chunk. So we divide our sentence like into chunks, fewest number of chunks, where the words, the order of words will be identical. So it is done to evaluate or to penalize the word ordering. For example, in both generated and reference sentences, words could be identical, but the order can be different. So, for example, the generated caption will have no meaning because the order is completely messed. And to penalize such cases, we use this fragmentation chunk. And alpha, beta, and gamma are just the parameters. And finally, Meteor is calculated using this formula. So And let's talk about the dataset used for training. So there is dataset presented by Microsoft for this kind of test. So it has more than 10,000 of videos from YouTube. They are very short, like 10 to 15 seconds, and from different kind of categories. And each video is described with 20 sentences. So for each video, there are 20 reference captions. And when we train the model, we consider these captions, like 20 captions, as separate input to the model. So here's the distribution of training, validation, and test set. So here's the results. So our sequence-to-sequence model, for our sequence-to-sequence model, the best choice of optimizer was RMS Pro. And also I have tried different kinds of embedding layers, tried to use pre-trained GLOW dataset and train embedding with 40 of 256 units. And the best blue 4 score was for with embedding 256, and in Meteor score, he is even better than blue score. And for attention networks, the best optimizer was Adam. And also I tried different units. So remember, our attention mechanism consists of different dense layers to calculate context vector. So I tried 10 or 20 units in these dense layers, and the result shows that 20 units performs better. Um, so here, the blue 4 score is the same for sequence-to-sequence and attention network. However, in terms of Meteor score, our attention network performs better. The reason why this happens is because Meteor considers synonyms, paraphrase, and that's why when blue 4 score is small, Meteor is can be higher. Here's the results for the attention network. So this heat map shows for each frame, for each output, like the sentence generated by the model is a woman is shown as stroller. So for each output, what was the attention weight of the frames? Like which frame was like more important in generating this output. So for example, here I have frames. I haven't put all the frames, just some of them from frame 0, then 29 and to 39. And for example, for word woman, we can see that frame 0 is small, the attention weight value is small, but when it comes to frame 31, attention weight slightly increases. And from the images, we can see that at frame 0, we can see woman, like she's faded, but then by frame 31, we can clearly see woman. So it means when the model predicted word woman, paid more attention to these frames, frame 31, 32, 39. And for example, for word stroller, it paid more the highest attention during frame 0. Let's now look at the video, and I will show the sentences generated by both models. So just there's a person showing how to fold a paper, and his reference caption, the person is folding paper, and the results of sequence-to-sequence model, the person is folding a piece of paper, and attention network gave similar results. A person is folding a paper airplane. So we can see that both sequence-to-sequence and attention networks, they generated the sentences which are correct, but slightly different from each other, but the general meaning is the same as in reference caption. And next video. So this video and reference caption is woman showing how to cook. By the way, I need to mention that the dataset itself, the reference captions, can be wrong. They have some misspellings. They can be grammatically incorrect, and but we can see that even though the reference caption can be incorrect, our models generated the correct result. But for sequence-to-sequence model, we can see that the result is not that good. It's given like a woman is talking about a man. So yes, a woman is talking, but not about a man, about the food. So it's not correct. But attention network generated answer, a woman is cooking, which is correct. So by this example, we can see that attention network performed better and it gives better results. So to conclude my presentation, so two network types were introduced, sequence-to-sequence and attention network. They are very similar in terms of architecture, but attention network considers inputs, encoder inputs during generation of output by using attention weights. And we can see that, and we saw that attention network has demonstrated higher meteor score compared with sequence-to-sequence network. And for the future work, I think this task can be improved by the performance of this task can be improved by introducing multimodal network, where we process not only images like I did today, but audio too. So by adding like audio, we can maybe improve the performance of this task. Here's the references. So thank you. If you have any questions, I will be happy to answer.
Thank you very much, Akzharkyn. That was quite interesting. So the practical application of video description today is, well, hard to underestimate because there are so many videos shooting right now to CCTV cameras, security cameras all over the world. All the things that we shoot on our mobile phones every other day, and how much trouble it takes for us to find the proper video in our cell phone's album when we want to see some video of our kids among all other videos of us shooting fireworks that we never watch again. So the big question about is, since attention network allows to get better results, what about power consumption? Because it's on this scale, power consumption matters. What do you think about that?
Yes. So first, since attention network is more complicated than sequence-to-sequence, it can consume more power. But I tried to simplify it by, for example, changing the LSTM into gated recurrent unit, which has less parameters. So it means we just decrease the calculation. And also I try to minimize the number of units. So generally in papers, they use in each gated recurrent unit, at each time steps they use about 256 to 512 units, but here I use only 40 units. But yes, I think this model should be further optimized for edge devices like mobile phone. In this project, I tried it only on computer. So I think for mobile device can be, yes, need some optimization to decrease power consumption.
And also one more question before we move to our next speaker is about the complexity of preparing and training the model. Because as you mentioned, you've used a lot of images in order to train the attention network. And it might be challenging for certain applications to collect that kind of data set. What would you recommend in order to prepare the data set, and how full should it be? How big should it be in order to perform the way you showed us?
So the advantage of the dataset that I used from Microsoft that it has all kind of data, kind of video from different categories. But if we're doing it for example, for specific task, for example, for videos about cooking, so our dataset should be subject specific. So it depends. First, we should decide why do we need this video description. And second, the quality of the reference captions matter because, as I mentioned, even this dataset was prepared by Microsoft. The quality of reference captions were not so good. There were a lot of misspellings. There were some, as I said, that per one video there are 20 captions. Like means they were captioned by different people, like person, and some of the captions were totally irrelevant. And so I think a lot of attention should be paid on the structure of the sentences, so the training can be better and easier.
Okay, thank you very much. And just a second. Yeah, well, thanks for joining us. Have a good day, and we will shift to our next speaker.
Thank you.